So here's our video recap of week 3 for intermediate algebra. The rules of exponents. So here you can see if you're multiplying the same base, you add the exponents. As long as it's the same base, you can add the exponents. So w is multiplied by itself 3 times. So it gives you a 3 exponent or a third exponent. And 5 is multiplied by itself 2 times, so it's 5 to the second power. So as long as it's the same base that's being multiplied, then you just add the exponents. So these are all examples of multiplying the same base. And as long as you have the same base, you just add the exponents. Pay attention to where we have y times y to the third power here, and notice that one, the y, you don't see the exponent, is to the first power. So you have to keep that in mind. Now there's coefficients on the exponent, on the variable. So what we do is we multiply the coefficients together. The coefficients are the number that's in front of the variable. So like 2x to the 5th power. So the 2 is a coefficient. So we take that and multiply that 2 by the 3 there. And then we can put the variables together, the x to the 5th power and times the x to the 6th power, and we're able to add the exponents because of the same base. Here is the division rule. So the multiplication rule told us that if we're multiplying the same base, that we add the exponents. But in the division rule, if we're dividing the same base, we now subtract the exponent. So as you can see in that first example, x to the 24th power, we have x to the 24th power over x to the 20th power. So they're the same base, which is x. So when that is so, we subtract the exponents. But there's a second part to that rule where you may have a larger exponent in your denominator. So now the rule is you're going to subtract the, as long as you're dividing the same base, you subtract the exponents and wherever the larger exponent is. So if the larger exponent is in the denominator, then that's where you're going to do the subtraction of the exponents. Like in example 4, we have y to the 15th over y to the 24th, and y, the exponent is larger in the denominator, so we do the subtraction in the denominator. And what's going to be up top is whatever number is in front of the variable already. So we have y to the 15th, but that's really saying 1y to the 15th. So 1 stays up in the numerator. And that's why we get 1 over y to the 9th power, and so on. When we raise something to the 0 power, the value of it becomes 1, except for 0 to the 0 power. So 3 to the 0 power, the value of it, or its result is 1. Anything that's being raised to the 0 power, except for 0 to the 0 power, is going to be equal to 1. So if you look like in example 2, where we have 4x to the 0 power, y to the 2nd power, we're able to just cancel that 0 power out because it's going to be equal to 1 anyway. So, that would be saying 4 times 1 times y to the second power. And the same thing in this denominator, 8 to the 0 power. We were able to just cancel that out because the value is 1. In this example 1 here, we're now looking at multiple variables. In the first example, 8x squared over y times negative 3x to the third power y squared. So we can, like we did earlier, we took the coefficients and multiplied those together. So I took 8 times negative 3 and then put the x terms together and then add the exponents, put the y terms together and add the exponents. So as you can see, when we simplified it in the third row, just looking at the top part of it, is simplified to negative 24x to the fifth power when we added those exponents, and y to the third power when we added the y exponents. So now we can use the division rule to, well, first we reduce that fraction. 6 goes into 24, or negative 24, negative 4 times. And then using the division rule, which is to subtract the exponents wherever the exponents exist, the larger exponent exists. So x to the fifth power minus the fourth power, that is. Y cancels itself out because it's the same thing, y to the third power over y to the third power. So that just cancels itself out because, anything divided by itself becomes just 1. So the second example is similar. Now this is another rule, the power to a power rule. When we're raising one power to another power, we multiply the powers together. So if you look at that first example, we have x to the fifth power that's inside of parentheses, and then it's being raised to another power, which is 6. It's being raised to the sixth power. So whenever we have a power inside of the parentheses like that, and then the power on the outside, that's where we use the power to a power rule and multiply those powers together. And the example where we have x to the second power y times y, and that's enclosed inside of parentheses, y, and that quantity, that product is being raised to the third power. So that third power, the power to a power rule will apply to both the x and the y, as long as there's multiplication between the x and y, which is so. So in that case, we get x to the second power times the third power, and then y to the first power times the third power, and then we see the result there. Same thing with fractions. If we are dividing variables, that power to a power rule applies to both the numerator and the denominator. So in this case, we'll get x to the third power and then y to the 5 times the third power over y to the 5th times the third power. And as you can see in example 2, there's multiplication between the coefficient and the y. So as long as there's multiplication between things there, that power will go to each one of those things on the inside. So the 6 power, the negative 6 power will be squared, and then the y to the 7th power will be multiplied by the 2nd power, 7th power times the 2nd power. So a power to a power rule, and then the denominator, the same thing happens. That 3rd power goes to both the y and the z. Here we're working with negative exponents. So wherever there exists a negative exponent, it can be made positive by moving the variable or number with the negative exponent to the opposite side of the division line. So looking at this first example that we have here, we are asked to simplify and write with no negative exponents. We were given x to the negative 3rd power, y to the 2nd power, over z to the negative 4th power. So all of those negative powers will have to move to the opposite side of the division line, and then they will become positive. So this negative x to the 3rd power will get moved down in the denominator. It becomes positive once you move it. The y to the negative 2nd power, we move it to the denominator, and it becomes positive when we move it. The z will have to go up, and then it will become a positive exponent. So anytime we're working with negative exponents, we have to make them positive in our final answer by doing that and moving them to the opposite side of the division line or the fraction line. Here, if you look at example 3, we have the inside being raised to the negative 2nd power. So what we do is we use the power to a power rule first. So, and that is taking that negative power to each one of those things on the inside, because there's it's all multiplication inside of the parentheses. So we take that negative power as a power to each one on the inside, using the power to a power rule, which is to multiply the powers. So now when we once we do that, we get 2 to the negative 2nd power times 4 to the negative 2nd, 2 to the negative 2nd power, and then x to the 4th power times the negative 2nd power, and then y to the negative 5th times the negative 2nd power. So once we do the actual multiplication of the powers, we get negative 2nd, negative 8, and a positive 10 power. So those negative powers will have to move to the opposite side of the division line. So this negative 2 power and negative 8 power will have to move down into the denominator, and then they will become positive powers. And here we evaluated 2 to the 2nd power. You never evaluate a negative power. You only evaluate it once you move it to the opposite side of wherever it needs to go. And then once it's a positive power, that's when you can evaluate it. Here we have scientific notation, and in scientific notation, whenever we're given a whole number, we're going to wind up with a positive exponent in scientific notation. So whenever we're given initially a decimal number to change into scientific notation, we're going to have a negative exponent. So in this first example, we have whole numbers 4,567. That's a whole number. So at the end of what we want to do is we put our decimal point at the end of the number, and we move it to the first, between the first and second number. We count how many places we moved, and then we write it as, in scientific notation, you know, as a, this right here, 4.567 times 10 to the negative third power. And then here, where we have not the negative third power, but it's a positive third power. Here I said whenever we have a whole number, we're going to have a positive power. So this was originally a whole number, so we moved it to change it to a scientific notation by moving that decimal between the first two numbers. We moved it 3 places, so that's going to be our exponent. And you know, as you can see, this next example, we moved that one 7 places to get it to between the first two numbers, the decimal point that is. So we're going to have that number 8.2760 times 10 to the 7th power. Now we're looking at a decimal number right there. So that decimal number, again, we're going to move it between the first two numbers, but this time it's going to go to the right, the decimal. So since we're originally given a decimal number, and we moved that decimal 2 places to get it between the first two actual numbers, we write this as a negative 10 to the negative 2nd power. So 6.1 times 10 to the negative 2nd power. So whenever we start out originally with decimal numbers, that's where we write a negative exponent to our times 10. So this one, in example 4, we move that decimal 7 places to get it between the first two actual numbers. So we write it as 1.78 times 10 to the negative 7th power. Here we're multiplying two numbers, and we're asked to use scientific notation to simplify it. So first we change those two numbers into scientific notation. So moving this, we moved it 5 places to get to the end here, between the first two numbers. And this one, we started moving this one, and we moved that one 7 places. So we write it in scientific note, both of them in scientific notation. And then what we do is we take the numbers 1.3 and 1.1 and multiply those together, and we put the 10 to powers together, because now we have the same base. And when we have the same base, we can use the multiplication rule to the multiplication of the same base rule to add the exponents. So it becomes 2.3 when we multiply the first parenthesis, and then using the rules for the same base, we add the exponents to get a 12 exponent there. And in 5.3 we have polynomial operations. Polynomials they have multiple terms in the form of a times x to the n power. So you know, and there's the different types of polynomials. A monomial has just one term. So 5x, for example, that's just one term. 5x squared y is one term. So those are just examples of one-term polynomials. And what separates terms is a plus or a minus sign. So if you look in the example for binomial, binomials have two terms. So, we have a plus sign there and a minus sign in this other example. So those are examples of, binomials, and, they have two terms. Terms are always separated by plus or minus. We have a trinomial here which has three terms: first term, second term, and the third term. The degree of a term is the sum of the exponents, is the sum of all the exponents in the term. So if we remember, a term is separated by plus or minus. So if we're looking at, what is the degree of this term, when we add the exponents, that will tell us what the degree is. So the first term has a degree of 5, because when we add the power that's with the x, which is 2, and add the power with the y, which is 3, 2 plus 3, we get a 5 degree. The second term, which is the 7x squared y, it has a degree of 3. We take the power that's with the x and the power that's with the y. We never write the one power with a single term, well, like a y, for example. But it's always a one power, so we have to make sure that we consider that when we're performing an operation or trying to understand it. The degree, now there's two different things. First is the degree of a term. That's individual. The first term, second term, if you look at the degree of each one of them. But the degree of a polynomial is the largest degree of all of the terms. So if we look at this example that I have here, we have 3x to the 5th power, y to the 4th, plus 3x to the 6th, y to the 2nd, plus 4y to the 7th power. And it's a trinomial because it has three terms. It's separated by plus or minus. The terms are separated by plus or minus. So it's a trinomial. The degree of the first term, if we look at that, we take the 5 plus the 4, it's a 9th degree. The degree of the second term is a 6 plus the 2. And then the degree of the last term is just 7, because that's the only variable there, y to the 7. So the degree of the polynomial, remember the degree of the polynomial is the largest degree of all of the terms. So the largest was the 9th degree. So that's the degree of the polynomial. And adding polynomials, basically, we have one polynomial plus the other polynomial. We know that they're individual polynomials because they're inside of parentheses. So one polynomial times the other, plus the other one. And we're just, what we can do in this case, since it's all involving plus or minus, we can take the terms that are alike and add them together. So as you can see, I've taken the x to the 3rd power and I put that one with the other x to the 3rd power along with the sign, the x to the 2nd power, plus the other x to the 2nd power. And then there's only one x term, so that one just 3x, negative minus 3x, so we just keep that by itself. And then the constant numbers, we put those together. So once we do all of that and put the like terms together, we can go and find the common denominator, as you can see here. And use the rules of combining like terms after we've had the common denominators for each one of the terms. And then 6.1, we have removing a common factor. So previously we learned about distribution. We distributed whatever was outside of the parentheses to everything on the inside. But now we look at reversing distribution, and basically that's going to be what's called removing a common factor. So here are the rules here. You look at each term to see if all have the same have something in common, or if all can be divided by the same number or variable. And the second rule, then factor out what is common. Bring it to the outside of the parentheses, that is. And then the third rule is if the same variable exists in all of the terms, then factor out the variable with the same or with the smallest power. So let's look at the examples here. Here you have, we look at the two terms, and 3 can be divided evenly into both of those two terms. So we bring that 3 outside of the parentheses. Since 3 goes into itself one time, we're left inside of the parentheses with just x, plus 3 goes into 6 2 times. So we're just left with 2y. And we do the same thing with, when we're asked to factor other problems as well. We look at each part of it individually. So we look at the coefficient to see if that will divide, anything can divide into all of the coefficients evenly. If so, we bring that to the outside of the parentheses. Then we look at the variable x, and if x is in all of the terms, then we can factor out the one with the smallest power. So in this case, we factored out x because we have x squared in the first term and x in the second term. So the smallest power is just x. So we bring that one outside. And then we look at y. Y is not in each one of the terms. So if a variable or if something can't be divided in each one of the terms, then we cannot factor it out, or we cannot do anything with it. So same thing applies to a problem like this here. We make sure that we look at each one of the things separately, such as the coefficient, the a to the third, the a variable, the b variable, and the c variable. We look at each one of them separately and make sure that we're able to factor out if they appear in each one of the terms. So the variables have to appear in each one of the terms in order for you to factor out the smallest power. All of these here uses that rule. In the fourth example, we have the common factor of b plus 3c in both of the terms. So we factor out b plus 3c, and then we open up another set of parentheses to multiply whatever was on the outside of the b plus 3c of both. So inside of that is going to be the 2a and then the plus 5. And the same thing happens in this next example. We see that the common factor is 2y squared plus 7. So we factor that out as 1. And then open up the other set of parentheses to multiply it to with whatever is on the outside. So the 3y goes in there, and minus 1 because there's an invisible 1 that's on the outside there. And in 6.2, carries on from the last example, factoring by grouping. Like we were looking at that last example, we saw that the two terms had, the common thing inside of the parentheses there. So just like this one here, we have 2y squared plus 7 that is common in both of the terms. So we factor that out into one parenthesis and then multiply it by what's on the outside of the other parentheses. So the 3y minus 1, because again, that's an imagine negative 1 really out there. So in factoring by grouping, we're given this problem 3a squared minus 9a plus 2a minus 6. And what we do is we group the first two terms, the 3a squared minus 9a, and we group the other two terms. Then we factor out each one of those terms individually, just like we were working with the other problems. So in this example, 3 will divide evenly into both 3 and 9, so we can factor 3 out. And then a is in both of the terms here, so we can factor out the smallest power, which is a. We had to remember to take whatever power that we factored out and subtract it from the power that's there. So this was 1 power, so we had to take 1 power away from this here, which left us with the a. And 3 went into itself 1 time. 3 goes into 9 3 times. And we factored out that a. So we do that same thing to that second term. 2 will divide evenly into itself, and it will divide evenly into 6. So we can factor that out. 2 goes into itself 1 time, 2 goes into 6 3 times. So we do that. So now we're at a point where we have the common factor of a minus 3 that we can factor out, and whatever was on the outside of the parentheses will come as the inside of the second set of parentheses that is being multiplied by. And this example uses the same technique. So factoring trinomials here, factoring, we factor the first term, which is the x squared. So x squared becomes x times x. So we open up 2 sets of parentheses to put one of the x's here, one of the x's there. And then we find factors of the last term that add up to the middle term. So in this case, the last term was 18. We wanted to find factors of 18 that add up to whatever our middle term is. So we tried 6 times 3, but when we add those up, they do not add up to the middle term, which is 11. So we have to try other factors that may add up to the middle term, which is 11. So 9 times 2, when we use those factors and check them to see if they add up to the middle term, they do. So since those are the factors, we take these and write them as plus 9 and a positive 2. And this, we check it to make sure that we get back the original by using the FOIL method. So these problems, other examples employ the same technique. And we factor the first term, x squared, which is x times x. We put our x times x in, and then find factors of the last term, which is negative 10. Factors of negative 10 that will add up to the middle term, which is -3. And as we can see, we tried different factors. We tried -2 times 5, but when we add those together, we don't get -3. So we had to switch it around to -5 times 2. And now when we add those factors up, they do add up to -3, which is the middle term. So we take those and put them into our as -5 and +2 into the other set of parentheses. Now this one deals with factoring trinomials that have a coefficient in front of the first term. As we remember, the last term, we didn't have a coefficient there. So, these are the rules that you're using to do that. So trinomials in the form of ax squared plus bx plus c. Now, what we do is we use this method called the grouping method, or it's also called the AC method. So we find A times C. A times C is whatever is in front of your x squared. So just like we have it here, A x squared plus bx plus c. Those are where you find A and C at. So in the example that I have here, we find AC time, which is 8 times -3, which is -24. Now we find factors of -24 that will add up to the middle term, which is -2. So all of these steps are what you are taking when we're solving this problem here. When we find the correct factors that will add up to the middle term, like we found here, we take that and we put an x with it. So here, like we have 4x minus, because this is a -6x, we just put our variable with it. Now we go and take this and replace the middle term with it. So instead of having that -2x there, we're going to replace it with 4x minus 6x, like we did there. And then from there we go on, we group. We group the first 2 terms together, and we group the last 2 terms together, and then factor out each one of those terms. And then we can use that rule where we have the same term, which is the 2x plus 1. We can factor that out as 1 in one parentheses, and then whatever is on the outside of each one of them, we put that in the second set of parentheses. So the 4x and the -3 will go in there, or the -3. So we're using this rule, the AC method rule, for the examples here, and they follow those rules to complete the problem of factoring. Then we have special cases factoring. We have the difference of 2 squares. So in the example that I have here, it's asking you to factor 16x squared minus 9. And we notice that both of these are perfect squares. The 16 is a perfect square and the 9 is a perfect square. And we have the minus sign there. So this rule can apply to that. When the rule is, now we can factor it as a plus b times a minus b. So, and this is how we look at it here. Actually, this should be a minus sign here. So that should be minus. All right. So because of the rule, 4 squared is 16, so A is 4. 3 squared is 9, so A is 9. A is 3 rather. So we have now A plus B. This is again, you know, your A squared, and this is your B squared. This is the B squared. So the square, and remember that x squared, you know, if we think about what that is, that's x times x. So that's why we have the x here and x here, x times x. So that's how we can look at, you know, these type of problems. The square root of 81 is 9, or in other words, 9 squared is 81. 7 squared is 49. So we can take that as A and plug it into the formula, which is there, which is 9, and then x squared we know is x times x. So 9x minus 7 and 9x plus 7. And one of them is a plus, the other is a minus, as long as originally, you know, we were given to it in the format of A squared minus B squared. So like we have here, A squared minus B squared. Then we have perfect square trinomials. And, you know, if we notice that we have problems written in that format, then we can use this rule to factor it. So there's 2 of them there, the A squared minus 2AB plus B squared. And then we have the same thing, but both have a plus sign in it there. So now the problem or the example that we were given is x squared plus 4x plus 4. So which is going to be more like, you know, this second part here. And we use that rule to factor it out. We look at the first term. The first term, which is A. So A is x because x times x gives us x squared. And then B is 2 because B times B, or 2 times 2, gives us 4. Or 2 squared gives us 4. So we have A and B. And now we check the middle with A and B from the formula. We try it with 2 times A times B to see if it gives us back what was in the middle before. And it does in that case. So 2 times A times B, A was x and B was 2. So 2 times x times 2 gives us 4x, which is what we have in the middle there. So now that we know that everything works out, we can use that formula to write it as x plus 2 squared. And this problem follows the same methods here, but we're using the first formula for perfect square trinomials in that case. And in 6.7, we're looking at solving quadratic equations by factoring. Here's the steps that you'll use to solve quadratic equations. The equation must be set equal to 0. That's the first rule. Factor, and then we set each factor to 0, and then solve each factor for the variable. Those are also called the roots. So those are, as long as your problem is written in the form of ax squared plus bx plus c, the equation must be set equal to 0 first. So if we look at this first example, the equation was not set equal to 0, so we had to move across the equal sign, the 7x across the equal sign to get it set equal to 0. Then we start to use the rules that were written there to solve this problem. So in the end, we want to find the two roots. The two roots that we found by setting each one of the factors equal to 0 was 2 3/5. And then of course you want to go back and check them. So we used the AC method with this. So the AC method was the last method that we talked about. So we used the AC method after we set it equal to 0 to get the two factors. And then we were able to get the two roots. And the last one is using a quadratic formula here. You know, we use a quadratic formula to solve a problem. Again, as long as it's written in the form of x squared plus bx plus c, we can determine, actually this should be 8x squared. So 8x squared plus bx plus c is equal to 0. As long as it's written in that form, you know, we can use this formula, which is the quadratic formula here, to solve for our roots. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And in this example, again, we had to get it set equal to 0, and then now we have the equation set equal to 0. We can determine what a is, what b is, and what c is. So in this case, a was 4, b was -7, and c was 3. So in solving it, we go and plug a, b, and c into the formula. And you have to be careful, because if you have negative numbers, you cannot confuse those negative numbers with the negative signs or the minus sign that's already written in the formula. So we use set of parentheses to enclose your negative numbers, so that way they will be able to calculate them properly. So here we have, once we plug everything in, then we have our our results, or our roots there. In the end, we separate the plus and minus. So here we still have our plus and minus, but we separated them there. And we were able to solve each one of them at that point. So that was the notes for week 3, intermediate algebra.